Hey everyone, and welcome back to part 2 of this video on the Bernoulli equation. In the last part, we covered the theory which Bernoulli's equation is expressing. Now we know Bernoulli's equation is simply an expression of the principle of conservation of energy for the three types of energy in fluids: potential, kinetic, and pressure energy. So here we have our three types of energies and their respective formulas here below. You'll probably recognize the potential energy formula and the kinetic energy formula. The pressure energy is simply the pressure contained in a given volume of fluid V. But this is an issue because we do not want our equation to depend on a given volume. We want it to work for all volumes. In fact, we want it to work for any mass, where you know mass is density times volume. So let's divide each of our terms by m, and we end up with this equation. This represents the amount of energy per unit mass in our fluid. Similarly, we could write an equation which represents the amount of energy per unit weight of our fluid, and we can do this by simply dividing each term again, this time by g. Because remember, weight equals mass times gravity, and we obtain the following formula. All these equations represent essentially the same thing: conservation of energy. However, in hydraulics, it is common practice to use this last version of the equation. This is because, if you notice, all three terms in this equation now all have the same units of meters. Although this may initially seem like an odd unit to be using, experimental equipment such as piezometers measure pressures in heights of vertical columns of liquid. So meters are actually a very simple and intuitive unit to work in. Now that we've changed their expression, we will no longer refer to these three terms as energies, but rather heads. What was the potential energy, energy due to height, we will now refer to as the static head. What was kinetic, energy due to movement, we will now refer to as the velocity or kinetic head. And while pressure energy is the pressure head. And this is simply what Bernoulli's equation is expressing, that at any 2 points along a streamline, the sum of these three heads must always make up a constant total energy. Now, it's important to remember to compare 2 points which are actually on the same streamline. If we were to attempt this comparison with a point at the center of this flow and then a point at the edge of this flow, the comparison would simply not be valid. Now, similarly to the pendulum in the previous video, although the total energy will remain constant at all times, the proportion of these three heads can change, depending on the behavior of the fluid. A fast-flowing fluid, total energy may be made up mainly of the velocity head, as we can see here, whereas a slow-moving one might have a very small velocity head and be made up mainly of the other two. The key being this principle of conservation of energy, meaning the total energy these three heads make up will remain constant throughout. So now that we have the terms used to express these three heads, which we can see on screen, we can put them together. And we finally derived our expression for the Bernoulli equation. So now that we have our expression for the Bernoulli equation, it's time to see if we can use it to solve a problem.